So this is the first sequences question I sent. So it says, on Alice's 11th birthday, she started to receive an annual allowance. The first annual allowance was £500, and on each following birthday, the allowance was increased by £200. Show that immediately after her 12th birthday, the total of the allowances that Alice had received was £1,200. Well, we know that in the 11th birthday, she got £500, and it goes up by £200 every year. So on her 12th birthday, she got £700. So immediately after her 12th birthday, she would have had £500 plus £700, which is £1,200. So that's the first one. Find the amount of Alice's allowance on her 18th birthday. So it says find the amount of Alice's annual allowance on her 18th birthday. So we're trying to work out how much she actually received on her 18th birthday. In order to do that, we should work out what n is. We know A is 500, and we know that D is 200. So when n is 1, that's her 11th birthday. And when n is 2, that's her 12th birthday. So when n is 3, that would be her 13th birthday. So if we want to know when her 18th birthday is, that will be when n is 8. So we now know n is 8. It's asking for a specific term. And when you're doing a specific term, you use un is equal to a plus n minus 1 d. So that's 500 plus 7 times d, which was 200. And if you work that out, that gives you 2,300. No, it doesn't. Sorry, it gives you 1,900. Next question says, find the total of the allowances that Alice had received up to and including her 18th birthday. So this time, because it says total, we're going to use SN. We've already got the information that we need. N is 8, A is 500, and D is 200. So SN, well, it's not SN, it's S8 that we're working out. N over 2, so 8 over 2, 2A plus N minus 1 times by D. So that's 4 times 1,000 plus 1,400. And if you work that out, that comes to 9,600. And that's a total amount up to and including our 18th birthday. Now it says when the total of the allowance has reached 32,000, so when the total of the allowances has reached 32,000, the allowance stops. Find how old Alice was when she received her last allowance. So we now know that SN, we don't know what N is, but we know that the total is 32,000. We know that A is 500 and D is 200. So we can say that 32,000, using the SN equation again, is equal to N over 2 times 500 plus N minus 1 times 200. What I like to do at this point is times everything by 2 so that this fraction disappears. So that's going to give us 64,000 on the left, and the N over 2 becomes N. Inside the bracket, we've got 1,000 plus 200N minus 200. And so that becomes 64,000 equals N times 800 plus 200N. And if we expand that, we've now got a quadratic in N. So if we bring everything to one side, and these numbers seem like they can be cancelled down, so I'm going to divide everything by 200. So n squared plus 4n minus, and if you divide that by 200, you get 320. We can factorize this. So n minus 16, n plus 20, which means that n is 16 or n is minus 20, but n can't be minus 20. Now n is 16, but they asked us how old was Alice. So if n is 16, go back to where you wrote down, oh yeah, n was 1, so it's 11th birthday, n was 2, 12th birthday, n was 3, 13th birthday. So from n to get to the birthday, we have to add 10. So then we can work out her Alice's age is going to be, she's going to be 26 years old. So that's the first question. Now let's have a look at the second one. This second question is what we call a recurrence relationship. It's given us what the first term is, x1, and then it's told us how to find the next term. Now recurrence relationships are related to the term or the terms before. So xn is equal to xn plus 1 is equal to xn times p plus xn. Find x2 in terms of p. Well, x2, if we think about it, x2 is equal to x1, p plus x1. And x1 was 1. So x2 equals p plus 1. And there's a 1 on the front, but that's just 1. So 1 times p plus 1 is p plus 1. Then it says show that x3 is this. So this is part A. I'll do part B over here. So x3. Well, using the same recurrence relationship, we know that x3 is x2 p plus x2. And x2 was p plus 1. So we've got p plus 1, p plus p plus 1. So that's p plus 1 times by 2p plus 1. If you expand that out, it gives you 2p squared plus 3p plus 1. And that's what we wanted. Now part C says, given that x3 is 1, find the value of p. So we know that x3 is 1, so we can use the equation from above. And we get 2p squared plus 3p equals 0. We can factorize the p out. And we get p equals 0 or p equals minus 3 over 2. Now p can't be 0 because it said it at the top that p is not equal to 0, so it can't be p equals 0. So p must be minus 3 over 2. Then it asks a really odd question. It says find x 2008. Now in a recurrence relationship, these are not these generally not geometric or arithmetic, so we can't use the UN equations or the SN equations. But what happens often is that there's a pattern. So let's see if there's a pattern this time. Well, we knew x1 was 1. We didn't know what x2 was, but we knew x2 was 1 plus p. And p we've just worked out as minus 3 over 2. So x2 must be minus a half. We were then also told that x3 was 1. Well, if x3 is 1, and we're going to sub 1 into the iterative equation, then x4 is going to be minus a half. That means x5 is going to be 1, and x6 is going to be minus a half. And so we can see x odd is 1, and x even, x sub even, is minus a half. Well, x 2008, well, 2008 is even, so x 2008 must equal minus a half. Right, so that's the second question. And the final question. A trading company made 50,000, profit of 50,000 in 2006. a model for future trading predicts that profits will increase year by year in a geometric sequence. Straight away, you know R, it's going to be an equation of R. So the model therefore predicts that in 2007, year 2, a profit of 50,000 times R will be made. Okay? So write down an expression for the predicted profit in year N. So year N, we know that A is 50,000, and we know that R is just R. Okay, and in year 1, it was 50,000. In year 2, it was 50,000 R. Year 3 was going to be 50,000 R squared then. So we can see there's a pattern forming that the power of R is 1 less than year. So year N is therefore going to be 50,000 R to the N minus 1. And that's the answer for that. Then it asks, the model predicts that in year N, the profit made, so it's the profit made in that year, will exceed 200,000. Show that N is greater than log 4 over log R plus 1. So we can say that this equation that we found in part A, which tells us the profit in year N, that's going to be bigger than 200,000. We can divide by 50,000, and there we've got 4. We know that there's a log 4 in the answer, so we're doing something right here. The N minus 1, we need to make N the subject of this equation. And so when the power is a variable and we want to find it, we need to take logs. So if we take logs of both sides, and I'm taking log base 10 because that's what the questions told us to do. In the answer, they've taken log base 10 as well. So bring the N minus 1 down using power law, and then divide by log R, and add 1. So N is greater than log 4 divided by log R plus 1. And that's what we wanted. Then finally, in part C over here, says, using the model with R equals 1.09, find the profit, find the year in which the profit made will exceed 200,000. So we're actually solving this equation that we showed in part B. And even if you didn't show it, you have the answer, because to show that, you already know what the answer is. So you can plug in 1.04 into this. 1.09 even. And if we work that out, we get N as greater than 17.086. N has to be bigger than this, so that means N has to be 18. Again, it told us to find the year in which this happened. So year 1 was 2006. Year 2 was 2007. So seems like we're adding 2005 to the number, to what year it is. So year 18, if we add 2005, that will be year 2023. And that's the answer to that. Okay, thanks for listening. Yeah, if you have any questions, please feel free to email me.